Good morning all. So today what we are going to see is a variable gradient method for construction of a Lyapunov function. So in the last session we had seen the Krasovsky's method for construction of the Lyapunov function. So here also, like the linear time invariant systems, what we had done, you had seen in the previous lectures, that we had defined for the linear time invariant system. I hope you remember that we had defined the matrix Q so that v dot of x is negative definite, and we try to satisfy this equation as A transpose P plus P into A as equal to minus Q, so that v dot of x is negative definite. And if we get a P which is positive definite, and we can define v of x, we can find v of x as x transpose P into x. So it was quite simpler. If Q is positive definite, and if this equation is satisfied with giving P as a positive definite matrix, then we can say that v of x is a positive definite function, and the whole system is a asymptotically stable system. In the similar pattern, for the variable gradient method, we are going to go in the backward direction. So here what we are going to do is we are going to define the gradient of the Lyapunov function v of x. And from v of x, we are going to determine the Lyapunov function v of x. And in between, what we are going to see is we are going to apply the theorem of the Lyapunov theorem and see whether v dot of x is negative definite. Negative definite. If it is negative definite, it is asymptotically stable, or at least we will see whether it is, here I will write it as, if it is negative definite, it is asymptotically stable, and we will at least see it is either negative semi-definite. So at least we can get a stable system. Okay, so that is the idea of the variable gradient method. So here we are going to arbitrarily choose the gradient of the function. That is why we have got the name as a variable gradient method. And from the gradient of v of x, we will generate the Lyapunov function by satisfying the Lyapunov theorem. Okay, so that is the idea of the variable gradient method. So now we will see what is happening inside this method. Okay, so all these things you know, but I will just repeat it once again. Given any system x dot is equal to f of x with the equilibrium point exactly at the 0, and this is an nth order function, so this actually is this x element of Rn, and here also this is x. Here I have put everywhere this now. So let us first choose a Lyapunov function v of x as a positive definite function. And then if the gradient of the function, what is the gradient of the Lyapunov function? We know that the gradient of the Lyapunov function is dou v by dou x. Okay, and what is the derivative of the Lyapunov function along the trajectories of the system? If this is equation 1, what is the derivative? It is v dot is equal to dou v by dou x into x dot. These are the things that we know. So now we'll proceed to the problem. So here the gradient of the function is defined as del v. This is vector. This is a vector here. So here let me give some notations here. Dou v by dou x1, let me call it as del v1. This as del v2, like that. So this as del vn. Okay, so this is how we are going to denote it. So if I write it as del vj, it means that the gradient of the function along the trajectories of xj, along the direction xj. Okay, so that is what it means. Okay, now once we have the what does the gradient method say here? Here we have to assume this function del v, we have to assume, and once we have assumed this function, we have to generate v of x satisfying the Lyapunov conditions. Okay, so how do we generate? So we have del v as dou v by dou x transpose, right? Dou x transpose. So how can we generate v of x? As we can generate v of x as the integral from 0 to x dou v by dou x transpose into dx. Right. So what would be this? So this can be written as v of x. So here if I write from 0 to of dou v from 0 to x, we can write this part as, this is nothing but 0 to x of dv. So this can be written as v of x minus v of 0. So what does it mean? This is the initial point and this is the final point. So we are trying to integrate, this is a line integral along the trajectories of the whole system. So coordinate, and this is a final position here. So let me consider a third order system here. This is x1, this is x2, x2 direction, then this is the third plane, x3. Okay, so let me consider a trajectory here, something like this. Okay, so this is the x position. That means it has it moves. If I here we are bothered only about the initial point and the final point. So we have moved along some distance in the x1 direction. So we have reached this position here, some distance in the x1 direction here. Once we have reached here, we then move to the x2 direction here, and then we can move up, right? So this is also the right way of moving. So in order to find the integral, we can also move in this direction. We can move along the x1 direction first. Then from the x1 direction, we can move to the x2 direction. From the x2 direction, we can move to the x3 direction. So we are going to write the integral in that pattern. So I can form it in this form, that is v of x can be written as 0 to x1. So this I will write it as del v. So when here I am moving along the x1 direction, we are only concerned all other terms are 0 here. All the other values x1, because I am along the x1 coordinate, moving along the x1 coordinate. So x1 is only there. All other terms are 0. Okay, all other terms are 0. So with respect to dx1, then what I am having integral 0 to x2. Here del v, what all terms are there here? We are in this plane, x1, x2 plane. So x1 and x2 are there, but all other terms are 0. Along the x3 direction, it is 0. Okay, it is 0. Similarly, if I can go up to the nth order system and then define it as 0 to xn del v of x1, x2, etc. up to xn dxn. Okay, here here it is dx2 plus. So this is how we can split the integral, because here we are able to split the integral because we are bothered about the initial and the final point only. So once we have defined a del v, then we can find out v of x from the integral, from the line integral of the system. So here what the important point is, the path does not matter here. Okay. Now what is the idea here? Now we can define, once we have found out v of x, this is how we can find out v of x from the gradient of the function. Now there are certain characteristics. Here we have to satisfy v dot of x as a negative definite function, that is the Lyapunov theorem. So now we will also define what is del of x, and then we will apply some conditions on it and try to solve the problem. Okay. So let us arbitrarily choose the function del v of x. So each term, each row can be defined as aij of x into xj. Okay, so I am going to write it as a11 into x plus x1 plus a12 into x plus a1n into xn. So we have arbitrarily chosen n by n coefficients. Okay, so here we have a matrix here, and we have to find all these coefficients if it's an nth order system. So there is another property of this del Vx in vector calculus. We have to generate v of x from the line integral of 0 to x of del Vx. In order to generate it from the line integral of the gradient function, uniquely there is a property in vector calculus, that means del Vx has to be the derivative of del Vx with respect to dx should be a symmetric matrix. Okay, so that means dou del V by dou Ax should be a, that means which is represented as phi, should be a symmetric matrix. That means these two terms should be same, these two terms should be same. Okay, that means this transpose should be equal to phi. That means phi transpose should be equal to phi. Okay, fine. So now what is the next thing that we have to see? If you look at this matrix, it is effectively the curl equation. That means del cross del V equal to 0. That means it has to satisfy the curl equation. You have seen this in your electromagnetic theory where Sharad sir had taken those portions here. So you can just go and refer to it and see this is effectively the curl equation, which says that dou del Vj, so I am writing here, so Vj by dou x I should be equal to dou del Vi by dou xj. So this is a curl equation that has to be satisfied. So how many curl equations has to be satisfied here? If this is an n by n matrix, so we have n minus 1 rows and n by 2 combination. So we have n by 2 into n minus 1 relations to be satisfied here. Okay, fine. Okay, so this is about, so we define, we arbitrarily choose this function, we try to apply this relation here, this much of relations here, and n by 2 into n minus 1 relations, and try to find out some of the coefficients of del V, and then we will also apply the Lyapunov theorem. That means V dot, we will also find out V dot. How what is V dot? V dot is equal to dou V by dou x into f dot, right? F dot, sorry, f dot, not f dot, x dot. So dou V by dou x into x dot, we will apply this, and we will impose a condition that the coefficients of this has to be negative definite. So V dot of x has to be negative definite for the system to be stable, and then go on choose the coefficients, and then finally we will go and check V. From this we will go and check V and see whether V is a positive definite function. Okay, so this is the idea of the variable gradient method. So we will see the procedures and one problem so that you will get to know how to do that. Okay, so I will just summarize the procedure here. First, we are going to choose the arbitrary function, gradient function in this form. Okay, here if you look at this matrix, you can see that everywhere the coefficients are represented as a function of x here. That means the coefficients also are functions of x. And here for simplicity, the diagonal terms, if you want, you can choose it as independent of x or constants. For simplicity, you can also make the problem complex by making it as not constants. Okay, so and also it would be better to choose the diagonal elements as greater than 0. If I am going to choose a11, a11s to ann's as constants here. So here everywhere I am going to take it as constants, and also these a11s to ann's as greater than 0. So this condition is imposed here because like if I have v of x as equal to something like 2x squared, x1 squared plus 2x2 squared plus 3x3 squared, that means that the del v of x would be something like 4x1 plus 4x2 plus 6x3. So if you look at these two relations, we can see that something which has a coefficient x1, the coefficients of x1s should be positive for v of x to be positive definite. Okay, so we will also keep this a11s and ann's as positive, so that once we go through all this procedure and come back to v of x, we may get a positive definite function. Okay, so this is one thing that we will be doing here. And the next step is we define del v of x, and then v dot of x. What is v dot of x here? V dot of x is dou v by dou x into x dot. What does it imply? It implies that this has to be negative. What is the condition, restriction on the coefficients? V dot of x has to be negative definite function, or at least a negative semi-definite function, okay, for stability. So near the 0 point, we are going to impose this condition for getting it as a negative semi-definite function. The next condition that we are step we are going to do is we are going to impose a curl equations here. Okay, so we are going to see whether the curl equations are being satisfied here, and we will get this much of conditions here or relations here, and then we will once we apply this condition, we may get all the coefficients here. We can assume some coefficients also, and then after that we are going to compute del Vx. From del Vx we are going to integrate it and find out V. And what is the last thing we have to do? We have to go on, check whether V is positive definite. Once we get this part as negative definite and this part as positive definite, then we can directly say that the system is asymptotically stable. That means step 2 and step 5 are very much important. Okay, here so now we will go and see a problem here. So once you do the problem, I think it will be easier for you to understand it more clearly. Okay, so this is a problem that we have chosen here. So this problem is from the reference 3 that I have given here in this references. Okay, so first step is to choose a Lyapunov function, the gradient of the function. Okay, so we are going to find the Lyapunov function from this gradient. So we will define it as a11x1 plus a12x into x2, a21x into x1 plus a22 into x2. See here, look here, I have chosen a11 and a22 as constants here, like the way which I said earlier. Okay, and I will also demand that a11 is greater than 0 and a22 is greater than 0, so that since it is these are coefficients of x1 and x2, I will choose it in that pattern so that my v of x which I get will be positive definite. Hopefully will be positive definite. Okay, now what is the step 2? Step 2 is to find the derivative of v of x. So what is v dot of x is del v of x transpose into f of x. Here I think this is not dot is not there. Okay, it is del v of x transpose into f of x. Okay, so this function we will write it here, and here this is the function here. So you can pause the video and then do this calculations here and see whether you are getting something of this form. See here I have rearranged the terms such that I will get it in this form. Okay, that means x1 x2 coefficients are grouped together, and x1 raised to, that means square terms are grouped together, and squares, so that I can easily find out v dot of x. Okay, so if this is v dot of x here, so what is this? If you look closely at this equation, what we can see, we want v dot of x, we are going to restrict conditions on v dot of x. We want v dot of x to be negative definite. Okay, so here x1 raised to 4, this part is negative, this part is positive. So I want this has to be greater than 0. So a21 of x should be greater than 0. Okay, what is the next condition? I'll write with a different color here. So what about this part? X2 squared is greater than 0. So this also should be positive. This also should be positive. What about this x1 x2 terms? If it comes in any function, it is actually an indefinite function unless we can write it in some form, x1 plus x2 the whole squared or something like that, or x1 minus x2 the whole squared. So this we have to avoid this. So in order to avoid this, the easiest way is to make the coefficient of x1 x2 as 0. So we will make this as equal to 0. So we have 3 conditions here. That is, I'll copy this this whole thing to the next Control C. So here to the next slide here. So I have this relations here, v dot of x is equal to 0. So here I have v dot of x is equal to this. Okay, so now what are the conditions here? A21 has to be greater than 0, of x has to be greater than 0, and if you look at this term, A22 minus A12 of x should be greater than 0, which implies that A22 is greater than A12 of x. Okay, is that fine? Okay, now if you look at this is a constant, so it's definitely this also should be a constant. We are taking the difference of that, this should be a constant, so we will make this also as a constant and say that this does not depend upon x, so this is also a constant. A22 is greater than A12. So let me choose A22 as some 4. Let us choose A22 as some 4, and A12 is less than that, so let us choose it as some 2. Okay. So what is from this relation, what is A11? So we got this, and we want A21 of x as greater than 0 for all x, right? Of x as greater than 0 for all x from the second one. So that condition we will see. Okay, what about this term? So I will write this as A11 should be equal to, so the first, this is the first one, this is the second part, and this is the third part. A11 is equal to A21 of x plus A22 x1 squared. Okay, so we will see. Now we will go and apply the third, we'll go to the third step. So we got this relation. So we will see what is A11 and all those things. Okay. So we will go to the third step. So we do have some more relations so that we can find out these terms. So we can go to the step 3. What was the step 3? We have to apply the curl equations. In order to apply the curl equations, we should have dou v j, sorry, how many equations are required? First of all, n by 2 into n minus 1. This is a second order system, so we need to have only one relation here. Okay, what is that relation here? Dou del v1 by dou x2 should be equal to dou del v2 divided by dou x1. Okay, so what is del v1? Del v1, a11 into x1. a11 into x1, this is a11. So you can write it as a21x into x1 plus a22 into x1 cube plus x1 cube plus a12 into x2, right? So a12 is 2. It is 2x2, right? Oh, sorry, this I have given it as 4, so I will put it as 4 here. So this is 4. And what is del v2? Del v2 is a21 into x1 plus a22 into x2. So I can write this as a21 into a21x into x1 plus a22 is 4x2. Okay, so this is what we get. Okay, so what is the relation here? Let us try to find out the relation here between these two. So derivative of del v1 with respect to x2. What is this? So a21 can have terms with terms in x2. So I will write it as dou a21x by dou x2 into x1 plus this does not matter here, this gets cancelled here, so this is 2 plus 2 should be equal to, what about this? A21, here I have to divide, find the derivative with respect to x1. So this is dou a21x by dou x1 into x1 plus a21 of x plus this is equal to 0. So this is the relation. So if you look closely at this relation, what you can see is that dou a2x by dou x2 minus dou a21x by dou x1 into x1 is equal to plus 2 is equal to this. So if this terms are something, so we have a constant term here and also a21 of x here. So if I want this constant to satisfy this equation, a21 should be a constant. So I have to make a21 as a constant here. with assuming that these two this is equal to 0, this is equal to 0. Okay, so I can take this implies that a21 of x is a constant here and it is equal to 2 here. Okay, so finally I can have del v as 2x1 plus 4x1 cube plus 2x2 2x1 plus 4x2. So now what is the next step? Next step is to find out. We got all the coefficients here from by applying the curl equations. Okay, now we will go on to the fourth step to compute to generate the Lyapunov function. So we can have generation. So we can have what is v of x is equal to integral 0 to x1 del v1, x1 is there, x2 is 0, dx1 plus integral 0 to x2 del v2, x1 and x2 are there with respect to dx2. So what is del v1? What is del v1? We will go and see what is del v1. That is 2x1 plus 4x1 cube plus 2x2. So I will copy this here so that I need not have to come back here. Control C. So I here. So I have here that is 1 second. When I copied it, I don't know whether I have done any mistake. Yes, I have done some mistake here. Okay, it's okay. So it is 2x1 plus 4x1 cube plus 2x2 dx1 plus here there is a 2 here plus integral 0 to x2 2x1 plus 4x2 dx1 dx2. So this I'll rub off. Okay, that's it. Okay, now you have this. So here x2 term is 0, so this I can put it as 0. Here both are there. So what is the integral of this? So I can have here is 2x1 squared by 2 plus 4 x1 raised to 4 by 4 plus 2 x1 x2 plus 4 x2 squared by 2. Okay, fine. This and this gets cancelled. This becomes 2. So I can write this as x1 plus x2 the whole squared. You have to rearrange these terms. You have to take x2 squared plus x2 squared and make it in this form, because I don't want this x1 x2 to lie here. So this would be x2 squared plus x1 raised to 4. Fine. Okay, I got v dot of x, v of x as a positive definite function, Okay, fine, good. I got v dot of x as a positive definite function, and then I think I have missed out something here. Step. Okay, integral was this. Okay, integral was this, and this was the fifth part. To checking whether it was a positive definite function or not was the fifth part. So v of x is a positive definite function, and we also got we had imposed conditions on v dot of x to be a negative definite function. So let us go and verify whether it is true or not. We will go to the second step, and so from here we will go and check whether v dot of x is a negative definite function. So we will see here. So we had imposed this condition here and applied it over here, and then we can plug in a21 as 2 and this as 4x1 squared and apply it here and make a1 in that form, so that this term becomes 0, and this is definitely 2x1 raised to 4. So this term is also a negative definite term. What about this term? This term is also negative because this is 4 and this is 2. 4 minus 2 is 2. So this term is positive. So v dot of x is a negative definite function. So definitely, so what can we conclude from this? We can say that from del v, we have imposed conditions on v dot of x to be a negative definite function, and from that we got v of x as a positive definite function. So our system is asymptotically stable. Our system is asymptotically stable. Okay, fine. Stable. Okay, that's about the variable gradient method. Okay, so I have given here two questions. This question is from this Latin text. It is not easy as you think. You have to work a little bit on this, and this question is from the Khalil text. So you have to try to do these questions and look at it and then work on this problem, the solution. So here also some assumptions are being made on the arbitrary functions. That means some are made as constants to get the results. Okay, so to easily approach to the solutions. Okay. So this is about the variable gradient method. You can refer to it in the following textbooks. I have also given the page numbers so that I want all of you to read the text at least once. And this is the paper which I will send you, from which I have taken the problem where some problems have been discussed. And you can also see the construction of Lyapunov functions from Professor Radhakant Padi's YouTube NPTEL lectures. So there also one or two problems have been discussed. Okay, if you want, you can look at it also. Okay, thank you. In the next session, we will see the invariance principle of Lassalle, and then we will wind up the third module. Okay, thank you.